Okay, today we're going to talk about angular and linear quantities, and so we're going to review our linear quantities, or review what we covered last time just a little bit before we move on. So with a review of angular, which we also sometimes call rotational. Okay, these are pretty much interchangeable terms. Angular and rotational motion. All right, we have this object. And if this is our axis of rotation, then we have, we have a place here, and as it rotates, it moves to here. And this, so we would call this angle theta initial, and this angle theta final, and so the difference between the two is going to be would be our change in our theta, which would equal, of course, theta final minus theta initial. All right, that's how we get our angular displacement. And then if we take our time derivative of that, this happens over a period of time, and that's delta theta over delta t is going to equal our average angular velocity. All right, but then if we take the limit of this, of delta theta over delta t, as delta t approaches 0, this becomes our omega. This becomes our instantaneous angular velocity, which is omega. All right. Then we can do the same process as our velocity changes. We take as their change in omega over a change in time equals our average angular acceleration, and we take the limit of that as t approaches 0, delta t approaches 0, and then we wind up with our angular acceleration. So it's the same process that we have with displacement and regular velocity and linear acceleration, except now it's angular displacement, angular velocity, angular acceleration. They are analogous variables. They're treated exactly the same way. We even have the same equation. So if we start with our linear equals v equals v naught plus at if our acceleration is constant. If we look at our alpha being constant, okay, then that winds up with that gives us an omega equals omega naught plus alpha t. And you can do all of the other kinematic equations. They look exactly the same, and you did them on the last unit, and they're exactly the same. You just switch alphas and omegas and thetas with x, v, and t, or x, v, and a. And time, there is no alternate unit for time. Time is time, and yeah. And whether or not time is a vector is a whole other discussion. Okay. What we do need to do now is we need to relate our linear speed. We need to relate our linear speed to rotation. So all right, so we're going to draw our body again. Okay, something similar to that, where we have, except this place, we have this right here. This is a position, right? So we can call this Ri from the axis of rotation, and this point right here would be R final. Okay, as we go from Ri to R final, this right here is our delta r, right? As we go from initial to r final, the change, Ri plus delta r gives us Rf. Yeah? Okay, that's, okay. Well, what we also have down here is this is our delta theta. Okay, the angle in between, our initial position and our initial position vector and our final position vector is a delta theta. It's our change in our angle. Well, the other thing that happens here is this delta r is a straight line, but if it rotates, it's really done this. That is the path that is traveled is along this little circle right here. Let's zoom in a bit. Okay, so this circle right here is actually the path that this point in space will take, and it's a little bit longer because it's on the curve. It's a little bit longer than the actual magnitude of delta r. However, well, at this time we need to kind of go into radians a little bit. So if you guys remember what a definition of a radian is, we can determine how many radians or something. It's the circumference divided by 2 pi gives us what the value of a radian. But what it really is, it's the length of a radius laid one radius of arc length. It is the angle subtended by one radius of arc length. Ooh, math words there. Okay, so if you take an actual length of radius and put it on a string and you wrap it around a circle, the angle that marks out is our 1 radian. Well, we get that. We do a general term with that, so our theta is equal to our arc length divided by our radius. Okay, where this is arc length, and this is radius. Okay, now, here's where it gets kind of cool. Let's say this is really small. That instead of having this big old delta r, we have a very small delta r. Well, S, our arc length, is really close to delta r if delta r is small. Okay, if it's a really small value, then S is pretty much equivalent to, or arc length is very close to the value of delta r if it's small. And so, okay, if we take this and we have, this delta r, if we make it really small, then it winds up that dr is the same thing as ds. Yeah? That the change in our position is the same thing as the change in arc length. Infinitesimal change. Yeah? Or conceptually, are we okay with that? Nudge. Okay, 2 thumbs up in the back. Thank you. Thank you, Omar. All right. So, we can rewrite this. I want to rewrite this up here. And we're going to rewrite this as theta equals S times 1 over r. All right? Because r isn't going to change. If we have an object that's rotating, the radius isn't going to change. If we have a point, if we have this point right here, and this point is traveling in a circle, the radius doesn't change. Okay, just where it is going to change. So, this theta is going to equal S over 1 over r, and we can rewrite this. We take the time derivative of both of these. We get d theta over dt is going to equal 1 over r ds dt. Well, what's d theta dt? We defined just a minute ago that d theta dt is omega. That's our angular velocity. Okay? S is a length, right? It is a linear distance. So ds dt is actually No, if it's velocity. It's okay. So if this is the length, this is the change in actual linear distance divided by time. Okay, that's going to be our velocity. So this winds up being 1 over r v, or v over r. So omega equals v over, or another way of writing this is, and it's simpler to do this, is we move the r to the other side and we get v equals r omega. Okay, and that's how we relate our speed to our rotational speed. And this should make sense. And here, this is an important distinction here, because we've got, here's a rotating object, and imagine we've got, we've got this going on. P1 and P2 are rotating along this line. P1 and P2 are rotating along the same length, right? Or they're rotating at the same angular velocity, right? They are subtending the same angle for every unit of time. However, one of them is moving a lot farther, a lot faster than the other one. Okay, and so the further away you are, the longer your radius from your point axis of rotation, the faster you're going to, the faster your linear speed is going to be. Okay, and that should make sense now with what we have here. That if omega stays the same, then our linear velocity is going to depend on how far away from the center we are. Right? If our radius is longer, with this staying the same, that's going to increase our velocity. Okay, if our radius gets shorter, it's going to decrease our linear velocity, even though the angular velocity stays the same. Yeah? We're good? Okay. Okay. That's why little things can spin really fast. Okay. It's also the same idea as one of the theories is for artificial gravity. When we start spending time out in long distances of space, if we travel to Mars, okay, astronauts are going to need artificial gravity because it takes months and months to get there, 6 months to get there, another 6 months to get back, with our current propulsion abilities. That's a long time for astronauts to not have to fight against gravity. Our muscles tend to atrophy just because we're not standing up against our Earth's gravitational field. So what they're going to do is they're going to spin the spacecraft. And the larger the spacecraft, okay, the longer the radius out to where the spinning would be, the lower the angular velocity has to be in order to maintain the same acceleration due to gravity, the same centripetal acceleration. Okay, if the craft is really small, then you start dealing with, let's come back over here. Okay, then you start standing here, and to get the same centripetal acceleration, okay, your spacecraft has to spin really, really fast. There's a problem with this, because people are not points. People are not, people are tall-ish. Okay, there is an acceleration gradient. Okay, if you are standing on the edge of one of these, that your head would have a different linear acceleration than your feet. Okay, the smaller the circle, the greater the gradient in gravity. So your blood would pool to your feet faster if you're in a smaller rotating craft than if you're in a great big one, because now all of a sudden your 5.5 to 6 feet of astronaut, or the 5.5 to 6 feet difference between your head and your feet, okay, is going to be minimal compared to the size of the circle of rotation. Does that make sense to you guys? Okay, it's an additional sort of thing if you want to talk about the spaghettification, which is becoming the clinical term of the tidal forces in a black hole. So if you enter the event horizon, okay, if your feet go into the event horizon and your upper body doesn't, okay, you'll become spaghettified, and it will stretch because there is a gravity gradient between your feet and your head, and as you move in, you would eventually get stretched further and further because the accelerations due to gravity of your feet okay, would be greater, assuming you jump in head first, or feet first. If you jump in head first, then it would go the other way. But yeah, if you belly flop across the vent horizon, then your front side, then the effect won't be as much. But all right. So, anyways, we may or may not actually get torn apart if we go into a black hole. So we can so here's our velocity relationship to our rotational velocity. Up here, we can do the same thing with the r, and our s, our position, okay, or our linear speed. I'm sorry, our linear distance is equal to r theta. Okay. And then if we take this one and we take v equals r omega and we d dt both sides, right? Okay, so dv dt is going to equal acceleration, and then d dt of r omega. Well, r is a constant, so it's just the derivative of the omega, and that becomes alpha a equals r alpha. And these are the three rotational equivalents. However, there's one more. This is the tangential acceleration. Okay, we still need to talk about centripetal acceleration, and so it's a little bit more. We know that it's centripetal acceleration equals v squared over r. But what was v? Okay, it was this up here. So this becomes r squared omega squared over r. Cancel the r's, and our centripetal acceleration equals omega squared r. And this is our centripetal acceleration. So these right here, these are our four. Yeah, our. These are our four rotational to linear conversions for this. There is another one, and it's kind of messy. Okay, and it's pretty straightforward, but it's kind of for intensive purposes. We kind of need to go through it. The overall acceleration, because what we have here is if we have our acceleration, we have AT and we have AC if we have an acceleration. So what is going to be the vector of that? Well, here's acceleration. We add the two vectors together. We need to find out what this overall magnitude is. Well, it's just like you're converting a magnitude. So our total acceleration is going to equal the square root of the two accelerations squared added together. So it's going to be r squared alpha squared plus r squared omega to the fourth. And we can factor out the r, so it's going to be r times alpha squared plus omega to the fourth. And this is the magnitude of our acceleration. Okay. And that is the end of that.